Okay, this is the extracted directory for LANSE version 1. I'm going to open up the solution file. So the place to start is program. If you just run the executable, you're going to need to set a path for your working directory. You create a non-orthogonal SVD object. This is for an A times A transpose matrix. And then you run the SVD. Some of these parameters here on run are the number of eigenvalues you desire, the number of maximum LANSE steps you'll take, and then the sample lag. Basically, you can request as many values as you want. You could request 500. Who knows how long it's going to take for you to get 500 depending on the size of your matrix. So the max LANSE steps will terminate at the maximum step no matter how many values you have. Lag is how often we'll check for the desired number of values. So at step 500 you check and you see if you have 300 values. If you do have 300 values, you stop. If you don't, you go for another 500 steps and check again. And obviously these are all parameters that you can tune. It makes sense to not check every step if you've got that many values, because then you just waste your time checking to see. Usually it's pretty obvious how fast you're going to converge. And then you write out your SVD output. In this case you're writing descending, so this is just the order of the values. And then if you want to test, there's compare to spaces from disk. So if you want to compare to like ARPAC or Octave, you can compute an SVD with that, then compute an SVD with LANSE, and then compare the two with this if you so choose. So let's look at this guy. Go to definition. So it's not the tidiest thing in the world, but you can see there are groups for some of these functions here. So the thing to look at is run. The first thing you do is create a compressed column matrix. There's some comments there. This is a little bit strange if you've never seen it before, but once you see it, it makes more sense. But basically you represent your matrix as 3 arrays. Some of the arrays are the coordinates of the cell, cell values, and one array is just the actual values within a cell. Big thing about compressed column matrix, is it a zero-based matrix or not? This is kind of important for getting stuff from MATLAB. And yeah, this is basically it. So some of these parameters you'll really never want to change. This is one right here that you may want to change. When you try diagonalize, you create some kind of output matrices, and you can either store some of these to disk to use later for a big multiplication step, or if you don't feel like it, you can just throw them away and then you can regenerate them later, and depending on what you want to do, you'll make different decisions here. I typically find that it depends a lot on the size of the matrix. A lot of times I'll just say forget it and recompute them. It's really just up to you. If you have really fast SCSI disks, you might want to save the vectors. So the first thing you do is you tridiagonalize. So that gives you a tridiagonal matrix. You get the eigenvalues from that matrix. You test the eigenvalues for convergence. There's kind of some junk here to do that. So use the CATS test. What are my real eigenvalues? And then you can go on and get eigenvectors for those eigenvalues. And then the next step is to map the eigenvectors to the actual vectors you want, the left singular vectors. So this is the first step. This is that big multiplication step that I told you about before. You could get it from disk or not. And then you need to normalize those vectors, so divide them by the vector length. And then you're basically done. And for each one of these I could drill down, but I don't think it's really necessary. A lot of this code is written in kind of a .NET 2 mentality, so you have untyped collections like ArrayList, the stuff that I'm working out, so apologies for the mess. Hope it works.